guys afterwards are ready. Okay, I did not make copies for you guys. Not a whole lot to copy, really. So here's what I have. What I have for you, and I do have the solution for these, but I need your help with it. Here's a busway. Um, I hope you guys enjoyed the trip yesterday to Boston Scientific. You've seen a lot of busways, 2000 amp, but what is it, 1600 amp? Beautiful stuff, good stuff, big stuff. Um, things that make you excited. If you doesn't make you excited, maybe you should switch careers. If that stuff doesn't make you excited, well, you can. Too late, Chad. So if you guys like these things, we're gonna size a few things about busway. Now before your friend Chad is gonna get this stuff in. Okay, so I have a busway. My busway has an overconduction device, as they all do. I have a busway, have an overconduction device ahead of it, a cable that feeds it, and also a couple of disconnects. And I need to, number one that you need to size is the busway itself. See, that's pointing to the copper or aluminum, the overconduction device, and the feeder. Exactly like we have done, guys, with the example. So I'm going to go over the solution for you. So I have, this is a P. I do have 4 motors, 20 horsepower each, 3 250, 5 30, and 6 150 horsepower. The voltage system on this baby, what voltage system? Is good point. What voltage here? The voltage system, let's just say the volt. We need the volt. Volt equal 480 volt 3-phase. Typically 480 3-phase volt. Cool. And we need to size that. We need to size that. So here's what I would like you guys to do. Any comments about what we have? How many we have? We have 18 motors, right? 18 motors plugged into this busway, exactly like you saw yesterday. Any question, guys, about the given? 480, size the busway, size the feeder, size the overconduction device. Piece of cake. And this is probably the first time or last time you hear Chad talk about these. Okay, cool. So here's how I do it, guys. I go right directly next to it. And the way we size it, the easiest way is to go find a full load current. So let's go find the full load current. We need to go to table 430.250. So I'm going to write table 430.250 under 480 volt. Remember, the voltage is 480. And we have been there. I don't want to go to the code because we have been there and do a couple of times, my friend. So we find the full load amp. The full load amp for this baby is 27 amps, and do not forget to multiply it by 4. Anybody understand? Can tell me why 4? Why we're multiplying it by 4? There's 4 of them. Cool. Everybody understand what I did? I got the full load amp, 27. I times it by 4. Okay. Next, I have 25. The 25 horsepower is actually, then the mix is the same. Piece of cake. I have 34 amps. Don't forget it's an amp. Multiply this baby by 3. Piece of cake. Come over here for the 30. I have 40 amps. Multiply this baby by 5 because I have 5 of them. And the last one, guys, I do it kind of slightly separate. The code says you take the largest, fattest, fluffiest motor, right, and multiply by 125. Which one is the fattest, fluffiest motor? 150. But I have 6 of them. So I'll take one of them, multiply by 1.25, the rest of them at 100%. The way I do that is I take 180, multiply this by 5, right? And you're going to know why 5, and then 180 multiplied by 1, multiplied by 1.25. Everybody understand what I did here? I split the largest motors into 2 sections. So I took one motor out of the 6 and I made it my largest motor. Can I have thumbs up, Chad? We understand what you did. We took the one largest motor. So Jeff, if you add the 5 to the 1, that'll get you 6. That's the number of the motors that we have. Okay, so piece of cake. Add them all up. Don't forget to use add, multiply, add. We do them all. I came up with 150 0.35 amps when you add them all up. That's what I came up. Anybody came up with something different that can challenge me? Not in the parking lot, here. Any question, guys, about this? Straightforward. Joe, my friend, you guys are notoriously famous of using at Egan, the busways, risers all the way and feeding. Did you guys see that 2000 amp bus duct that went down the hallway yesterday and feeding all these equipments? So that's basically very similar to this. That's how they size it. Okay, so that's the first calculation you need to do. Then you need to, so the first thing I need to do is find the busway. So the busway 1535 amp. Since I don't make busways, I always ask you guys, my friends, to go to DeWalt. Go to DeWalt 3-13, I believe. 3-13, please correct me if I'm wrong on that. And your standard carry, my friend, if you go to that, please write yourself a note for the test. Where to go, how to find them, and that will give you a 1600 amp busway at 480. Typically, it will be 600 volt rated. All of them are 600 volt, but you can use it 480 or 280. Any question guys about the size of the busway? So that will constitute the size of phase A, phase B, and phase C. The size of phase A, phase B, and phase C, right? The copper, the aluminum, or the copper inside it. Any comments, guys? Any questions about that? Any comments? Any questions? Is that straightforward? No gimmicks, nothing. If you know how to do that, you get your D plus and move on. Overcam detection device. The overcam detection device, guys, like I told you, the way I would do it, I take the same amps, 1535 amp, take this one to the code now, 240.6 from NEC 2011. If you guys go to the next standard and go to the next standard is 1600 amp. So basically we hit the jackpot here. So my overcam detection device matches my busway. Doesn't have to, but this is the best way to do it, to make the overcam detection device match the busway, but you don't have to. My overcam protection device could have been 1000 here. Can I put 1000 amp circuit breaker to protect the 1600 amp busway? Yeah, it's not a good design, but I can do it. Okay. Not a single one of you guys asked me one question, Chad. But when we sized the overcam detection device for motors, we did it differently. You guys remember how we used to take the overcam detection device of the largest motor, add everything to it, and go down? If you do it on this system, because the system is so big, so many motors, it doesn't make a difference. It really doesn't make a difference the way we size it. Okay, feeder for busways. The feeder, what I do for the feeder, guys, I always say match overcurrent protection device on these. So I have 1600. I need to parallel, apparently, right? Parallel. I decided to use 4 runs. From the 4 runs, table 310.15 B16 under 75-degree column. From this table that you and I know, guys, you're going to have 4 sets because Chad wanted 4 here. You could have had 3 conductors because it's 3 phase, and 600 kcm THHN, unless you know otherwise, that's wet location. So that's my phase conductors. I want to do the neutral, guys, just in case. You really don't need to do the neutral, but I'm going to do the neutral just in case you need to do the neutral. The second thing is going to be neutral. Any question about the phase size? Piece of cake. Parallel. Neutral. The way I would do the neutral, I would take the 1600 amp that we size the phases at, 1600 amp. The first 200, what do you do with them? They're circle, don't leave them alone. Anything higher than 60, the 200, what do you do with it? Cut it by what? 0.7, an amp. See what I did, guys? I took the first 200 from 220, that's 60 watt. First 200, leave them alone. Anything higher than 600, what do? Chop them by 70%. Take advantage of the derating for the neutral. If you need a neutral, most of the time, guys, you don't even need a neutral. Okay, so if you do the math on this, everybody knows when you add them up and do the whole calculation, you end up with 1180 amp. That's your amp that you need to size your neutral at. Then I take 1180. I have no choice except to parallel 4 because I parallel the phase is 4, right? I need to parallel my neutral 4 because, you know, in this case I'm taking sets. And if you guys do that one, you're going to end up, where am I here? You're going to end up with 295 amps. You take this one to table 310.15 P16, and that will get you the following. I will write it right here. 4 sets, 1 conductor, and each conductor is going to go, thank you, sir, 350 kcm, T, H, and another H, and an N. So we went from 600 to 350. That'll give you a smaller conductor. If needed, most of the time, no need for neutral. Because they're 3-phase. In this case, as a matter of fact, do you see anything that connected to neutral? The example that I gave you, you probably would never pull a neutral there. Now the question would be, Darren, when would I pull a neutral? You know when they pull a neutral? If you have a riser downtown Minneapolis, 18-story building, and you need to take a 2,000 amp bus duct from the basement all the way from the basement of that building all the way to the 18th floor, and tap into that one to feed lighting panels. For wire? They're using there? Yeah. Absolutely. It depends what I don't know what they're feeding. They must have using the neutral for something. So if you're using the neutral, which typically the only time we use a neutral, guys, is light 277 for lighting system, or using it 124 receptacles or 124 lights too. Other than that, it would be a waste of money to buy a machine that runs single phase when you have a 3-phase system. So, but it could be. Okay, so we size that one. Okay, so these are the only thing I just said here is the conductors, guys. I'm going to write my conductors. So we talked about my conductor size. Conductor size. My conductor size. So here's your runs that you're going to have: A, B, C, an N, and a ground, each in one conductor.
Are we going to do a conduit?
I did not ask you, did I ask you about conduit sizing? I don't know if I asked you about conduit sizing. Let me just see. Would it be hard to ask you guys about conduit sizing? I don't think so. Feeder size, feeder, the busway size in AWG or KCM. Feeder size, I did not ask about the conduit. So, did not ask you about the conduit. But if I ask about the conduit, is it hard to size a conduit? Not really. Okay, so that's the second thing I want to size, guys, is the equipment grounding conductor. Equipment grounding conductor. That's piece of cake. You need to go to 250.122 table, and I have the amps for the overcomputation device is 1600 amps. If you go there, you need 4 sets of equipment grounding conductor. Each one of them is number 1 4 aught. So, long story short, your system is going to look something very similar to this. The equipment is going to be a 4 aught here. The neutral is going to be a 50 kcm. This is AWG, and all the phases are going to be, what is it, 600 kcm. Does that make sense? Every feeder is going to have these conductors. Now, if you guys, if it's an EMT conduit, do I need it? No. So, if I ask you about the conduit, guys, this in a PVC. I'm assuming it's going to be a PVC Schedule 80. I'm assuming it's going to be a PVC Schedule 80 because highly corrosive environment we're using. So, on the test, sizing, the neutral is a must. The ungrounded conductor is a must. The equipment grounded conductor is a must. The conduit is up to you. Did you guys hear me? I need to see these 5 conductors. The conduit, if you will size the conduit for me, I hope you would. But I'm not going to dock you for that. Any comments, any questions? Does that make sense? That's what you guys do as a designers, right? You know what? I did not size it to tell you the truth.
No, I'm just saying it's easy to see with 4 out. Okay.
Which, I mean,
I just wanted to verify that I was looking at it.
4 out, yeah. Did he come up with 4 out?
Yeah.
For 1600? Okay. So that's how your system is going to look like. Any comments, guys? Any questions about that piece of cake? Yes, no? Okay. Again, this will be the last time you're going to hear Chad talk about these sizing. If you get out of done without knowing how to do that, ask your friend Chad for a refund. Okay, load. The second example, guys, about generator size. Did I go too fast here? I'm sorry. Did I go fast on that one? Everybody's good?
That was question 1.
That's question 1. Yeah, question 2 is I have a load of 431 kVA, 483 phase. Look at the term that we're using, kVA, not kW. I need to size a gen, and I need to size the overcome protection device. So I need the gen size, I need the overcome protection device, and the conductor size. This is what we call it, and I also need the grounding electrode conductor and the main bonding or the system bonding jumper. Everybody can see that? I need number 1, the generator size, number 2, the overcome protection device, number 3, the conductor, number 4, the grounding electrode conductor here, and number 5, the system bonding jumper. System bonding jumper. And I think I gave you, did I give you guys sizes of the actual generators? I thought I gave you sizes, should be, and I asked you to put them in DeWalt. Yeah, I made you a copy. If you don't, make sure you get the copy for you. So I hope I size it right on that one. So I have 431. If you take 431 kVA, you take this one, guys, to the sheet that I gave you. I have mine in actually DeWalt. I wrote mine DeWalt 3-13. 3-13. But for you, it will be the sheet that I gave you if you have not written in there. So what did we say? This is the generator 431, 431, 431, 431. What did I come up with? I'm sorry, not 431. Yeah, 431, Chad. I came up with 438. Anybody came up with 438? The actual size based on the sheet that I gave you. So that will be 438 K. Well, I put them in 3-13. 3-13. Again, it's not there. You guys have to put them or the sheet that I gave you. Am I right here? 438. So that's the actual, that's just the size of the gen that you're going to buy. Again, Joe, we don't size the gen, guys. How do we size the gen, guys, with me? How did you size the gen last time? Software. You get the software. From the software, you find the kVA. After you find the kVA, then you start doing the sizing. Okay, overcome protection device. The overcome protection device, my friends. So I equal the overcome protection device 438K. Divide this by 480. Multiply it by 1.73. This get you 527 amps. We found the amps for the conductor. That's step one. Step two, we multiply it by 1.15 times, that's what I would do. Multiply by 1.15, multiply the 527. When you multiply them, you end up with 606 amps. And if you take this baby to 240.6, you go next to the next standard, which is 700 amp. I got my 700 amp. Cool. Went up to next standard 700 amp. Where did the 115 came to be, guys? Kind of interpretation of Article 440.13, 440.13. Okay, now I have an overconduction device size. I'm going to go size my conductors to match it. See how easy that is now? You can size your conductors to match it.
So that was going to be times 1.15.
Yes, 1.15. That's coming. You guys remember that? I got that one, at least by interpretation, from 445.13. 445.13. Okay, move on next. Yes, no? Okay. All right. Jimmy, good. All right, generator feeder. Generator feeder, what I say, guys, match overconduction device. Go back. Sorry. My apology. Cool. Okay. The next, my friend, is gen size match overconduction device. So carry, my friend, my overconduction device was 700. So I have, and again, this one from the same thing, 445.13. All right, here's the 700. I don't want to carry a 700 conductor, so I divide it by 2, always parallel, 350 amp, all the way from here to, you know which table? Table 310.15, B16. You're going to get sick of Chad writing this table. Somebody forget that table after you graduate, guys. That'll be disaster. 75-degree column. And when you go there, you're going to have two sets. Each one set is going to have 3 conductors because of the phases, and each one of them is 500 kcm, T, H, H, N, unless you know otherwise. If they're outside, Aaron, what would the insulation be? THH, W. That's all. Now, do I need a neutral with the generator? Of course, all the time. Now, this is where I must size a neutral. Did you guys see that? The neutral with the generator, you have to, because you need to get the 277 voltage. Okay, for the neutral, piece of cake, what I do for the neutral, guys, exactly like we did, we take the 700, take advantage of 220.61, advantage of the neutral, and EC 2011. We wrote this many times. If you go there, the first 200, leave it alone. 700 minus 200, multiply these babies by 0.7 and add them up. Don't forget to add up. And that end up with 550 amps. Here's my neutral amp, the rated neutral amp. Then I can find my 550 divided by 2. That will get me 275 amps. And again, go size to the same table. Table 310.15 B16, 75-degree column. And gentlemen, you're going to end up with a neutral, 2 sets again, 2 sets. Each one of these sets is going to be 1 conductor, 300 kc an amp. Right? So I have a phase of 500 and a neutral 300. Typical, 1 or 2 steps below. That's very typical, guys.
appreciate you.
Thank you. T, H, another H, and N. Yeah, always insulation. Always insulation. Is that hard, guys? Piece of cake, Adam? Good. Now I can't pick on you. You're going to be a father, man. It's just. How many kids do you have, Andrew? 5? You said this at the beginning, and then you said this. That's 5 is a lot.
5 if you count the sheet.
Sheep. Okay. Oops, did they go too fast? I'm sorry. Did they go too fast? Jeff? No? Everybody's good? Okay, so that's straightforward, guys. I can't emphasize, I drilled that through you guys once and forever. We'll leave them, so hopefully when you graduate from here, you're good to go. Okay. The last thing, or the last 2 things we're going to do is grounding. GEC is grounding electrode conductor, right? For grounding electrode conductor, since we parallel, here's how we do it. You take the number of sets, 2, multiplied by the 500 kcm, equal this one to, of course, 1,000 kcm. Then you take the 1,000 kcm, take it to table 250.66. And from there, how many? 1, no sets, nothing. 1, 2, odd. Now, Jeff, do you remember yesterday when I showed you guys the grounding bar right at the, just off the ground? That's where that conductor goes, tied to that grounding bar. Everybody understand where that conductor goes? Why one of them, even though we parallel 2, Chad, it's only one conductor going directly and tied to this. It's not going in the conduit by itself. Did you guys see that grounding bar and the 500 kcm ground ring that they did around the building? I hope that will make you appreciate the bonding and the grounding that we're doing. Okay, the main bonding jumper is exactly the same thing we deal with it. So 2 times 500 kcm equal 1000 kcm. And then there is a question that you have to ask yourself though. So that then you take the 000 kcm to the same table, 250.66, and guess what you're going to end up with? One conductor, number 2 watt, AWG. Oh yeah, by the way, what's the insulation? This is AWG. This could be THHN or bare or covered. I just want to use THHN, but really it can't be bare. Did you guys see them, how they were black conductors labeled green yesterday, and some of them were bare conductors? Anybody pay attention to the grounding? Yeah. So they can be bare or insulated. Insulated will protect the conductors a little bit.
Why do you use 250.66 instead of 122 for the number 4?
122, because the code says so.
For the generators?
For the main bonding jumper, actually, can you guys erase this one? I'm sorry, this should be system bonding jumper.
I was talking about for number 4.
System bonding jumper, number 4. Because the code says so. The grounding electrode conductor is 250.66. If you go read 250.66, it tells you when you size it, go to 250.66 table.
Then when do we do the fuel electrical conductor for the EGC compared to the EDC?
Okay, let's go back to the picture. Very good point. Do you see that grounding electrode conductors coming out of the generator going to the ground bar that we saw yesterday? One conductor, solo by itself, not in a conduit, nothing. Coming out of the generator going to the ground bar, right? Like we looked at yesterday. Cool? The equipment grounding conductor will be coming from here. Yes.
Will be something that's coming along.
Yes, this is your equipment grounding conductor going back to the ground inside your switchgear. Does that make sense? Okay. I know it's a little bit confusing, the two of them. Okay, good point. And we sized it, right? We sized it. Did we size the equipment ground conductor for that gen? No, we didn't size the equipment. If you were to size the equipment ground conductor for the gen, guys, 700 kcm, see that 700 kcm? Go to 250.122. You got your equipment ground conductor. Really, not no gimmicks.
Two of them are gonna be the same, they're just wired grounded to two different places.
You mean the same size?
Yeah.
No, one of them is grounding the equipment, and the other one is grounding the system. And can you hold this discussion, because I do have, you're going to get sick of grounding the system versus grounding the equipment. I really do have a very good sheet that I give you guys next week or the week after, that we go over all the bonding and grounding and the difference between. If you just hold, just remember right now, one ground the windings, that's the grounding electrical conductor. The other one ground the frame. The equipment ground the frame.
So the system main jumper, bonding jumper is the one that, the system bonding jumper grounds the main,
The main, the windings, the windings.
that grounds the bonding.
Yep. Okay, any comments, guys? Any questions before I flip it to the second one? Any comments, any questions? Let's second and last one. Okay, so you're going to have 2 questions for busways and 2 questions for generators. Everybody understand that one? And 1 question for transformers. And Darren, my friend, that will be the last time you're going to hear Chet talk about this one. He will test you on the final, and guys, you don't hear about it again. We'll get you out of here. Okay, I do have a transformer. The impedance is 5%. It's 4160 on the primary, 48277 on the secondary. I need to find the feeders and overcompression device on the primary, the feeders and the overcompression device on the secondary, as well as 5 is short circuit. I'll give you guys a few seconds to sketch what you need to sketch. The transformer is fat and fluffy 500 kVA. Does that make sense? I have a primary of 4,160, typical. Secondary 48277, a delta Y, impedance Z5, kVA is 500 kVA, and I need to find the feeder and the fuses on the primary, the feeder size and the fuses on the secondary, plus the available short circuit. The available short circuit, number 5. 5 things, and then that's it.
That's total bank KVA.
Yes, good point. That's all of them. Do you see, it's just one, see how that blue box, it's one big fat 3-phase transformer. It's not a banked, actually. It's not like 3 single phase side by side tied together. This is one big 3-phase transformer. The reason why I picked this one, guys, for the test, because that's 99% of the time, that's what you're dealing with. You're dealing with this scenario. So I decided to put it in the test because that's why to put something that's highly unlikely you're going to see. We went over the banking, right? You guys remember the banking and the delta and all the stuff? That will be FYI only. I might need some of you guys to give me a hand here. I know for a fact because, okay, primary feeder. Shall we go? Everybody's good? Andrew? Adam, my friend? Okay. Feeder, primary feeder, typical, very typical, guys. When you do primary feeder, Jeff, you know you are on the primary, primary. Since you are on the primary, which voltage are you going to use, guys? The primary voltage. So that's, then you take 500 kVA, divide this one by 4, oops, not 480, 4160. 4160 multiply by 1.73. This is the modifier for a 3-phase system, and the amps for this should be, your amp should be 69.4 amps. 69.4 amps. Okay. Now in the past I used not to multiply it by 1.25, guys. It's a good idea. You can go there and size it right now. What I want you to do is be more cautious and add 25% for safety and for continuous load and all this good stuff. So coming here, I'm going to take 1.25. I haven't done that before on these. 69, that's what I need you guys to give me a calculation. Anybody has a calculator handy, please? So that's what I need your undivided full attention. 2 gentlemen or a gentleman and lady to agree on something.
86.8.
Second, 86.8 amps. Okay. Now the last thing is to take that baby. which is 86.8. I need somebody to do that too because I don't have the answer really. So I need you to go take it to table. Now which table? Remember, this is high voltage. So we don't go to 310.16. You need to go to table 310.60 C77 under MV-90. Can you guys go there? Could you please go there and find me? It should be three conductors, number. So I need, so that was, because I don't have the answer for the 186. So do I have two gentlemen to agree on that? Number 4. Any second? Sounds. Where am I here, Chad? Okay, there you go. Okay, so let's go 277C under. Remember, the voltage is what? 4160. Which set of columns you're going to go? The first set of columns. So the up to 5,000. When you go there, guys, I have 65. No, I can't go. So that will be 85. 86. I can't go. That will be 110. Number 4. Anybody came up with number 4? Yep. Number 4. Downing Thomas, huh? Number 4. Here's number 4. Now, what's the insulation though? AWG. What insulation? The insulation is MV-90. And that's where the difference in the medium voltage. If you put the insulation as THHN here, you're not going to hear the end of it from your friend Chad.
More insulation?
Yes, thicker, bigger, more insulation, shielded. The medium voltage, guys, yeah. THHN is good up to typically 600 volt. That's what typically we use it. Higher than 600 volt, especially at this medium voltage, you start using different insulation. Notoriously famous is MV, medium voltage. Any question, guys, about this? Okay, thank you. So that's my conductor on the primary side. Piece of cake, huh? Okay, secondary feeders. So I jumped into the secondary side. So I have secondary feeders. Now, the only difference here, guys, is on the secondary, secondary need to go to 500 kcm. Sorry, did I miss something? 500 kcm divide by 1.73 times, what's the voltage? 480. That will get you a healthy 601 amp, right? Anybody disagree with that? 601 amp. Then I don't want to carry a 600 amp, guys. Remember, when do we parallel? We parallel if you can't carry things in a 500 conductor or less. That's when you parallel. Or when your amps are 400 amp or less, you carry them with one conductor. More than 400 amp, almost always we parallel. Amps. Oh. Did you write this, Aaron? I didn't write that. KVA. Thank you. I'm sure you guys are. I'm glad that you guys got your milk this morning. Okay. Now here's what I didn't do in the past. I did not multiply by 1.25 because that's kind of a judgment. A lot of books do multiply by 1.25, so I want to multiply by 1.25 for safety. So I'm going to go 1.25, multiply this baby by 601. I need somebody to do the math for me, please.
756.
750. Oh, yes.
751 probably.
I need calculator.
751.
Oh, 751 amps. Can't guess if my wife likes to run on that. I guess you can take 25 of that number. Okay, then 751 divided by, let's parallel 2, right? 2 sets. Do me a favor, can you give me that? Divide by 2.
350.5.
350.5 second. They got you. 375. Any second? Can somebody second, Aaron? That's good? Okay. And then take this one to table 310.15 B16 under 75-degree column. That will give you two sets. You got two sets of how many conductors? Can somebody do that for me, please? That would be 500, right? Of three conductors. Number 500 KCM and THHN, right? Am I right? 375. Because 500 KCM can get you 380. Right? Can somebody check that? 380. That should be. You're going out of memory here.
Yeah.
500 KCM. Just to give you an idea, guys, if you don't multiply it by 1.25, you end up with a conductor 350 here. From 350 to 500, that's a big jump. So, okay, let's do the neutral. Let's do our neutral. So what I would do for my neutral, since I in neutral, guys, they don't, you know, since we added 25% on that one, I'm going to use the same amps here, 751, same amps after we modify it. And I'm going to take the first 200, remember how we do them? And the rest, what do you do? 751 minus 200. I really need somebody to do the math on it. Yeah? 0.7, add them up, will you?
585.
585 amps. Wow. You're the best. Okay, so then you take the 585, divide by 2. 293 second. 293 amps. Then you're going to take it to table 310.15 B16. And what do you get? Two sets of one conductor, each one of them 300. Can somebody check that? 293? 350? Okay. 350 KC and M and T, H and H and N. Done. Any questions about sizing the secondary feeder? So please always, why didn't we have neutral on the primary? Why didn't we size it? There is no neutral there. If it was a YY, do the same thing. Let me know when I can flip. Flip. Darren, you call it? Okay. All right, so primary overcap protection device fuses. We're using fuses for the primary overcap protection devices. Fuses. Looks like fuses here. So primary overcap protection device, and I will use fuses. Okay. So if you guys remember when we did that one, we said if you go to table 430, just want to write it down, table 450, not 30, not 3A. And from there, it tells you the following. Take 3, multiply by the full load current on the primary, because we are on the primary. And that will get you a healthy 208 amps. Then take your 208 amps, take it to 240.6, and that will get you 225 amps because they allow you to go up. Why do you go up? Because there's a note number 1, if I remember right, that tells you to go up, right? If you guys go to the table, if there's note number 1, it says, by the way, if you don't hit the standard, instead of going to the bar drinking, getting mad, right? All what you have to do is just go down. Or custom design yourself a fuse that's 208 amp. Busman will be more than happy to do that for you. For the secondary, guys, piece of cake. Secondary, same thing, 1.25. Multiply, the secondary is 601, because I'm on the secondary side. Get you 751 amp. If you go to 240.6, oops, let's do it the proper way. So then you take the 751 amp, take this one 240.6, and that will get me 800 amp. 800 amp. 800 amp. Piece of cake. Did I go too fast on that, guys? Yes, no? No? Okay. A short circuit is even easier. I short circuit. That doesn't even get close. When you get to the edge, it's really hard. I short circuit equal. Now I secondary, always. You always use a secondary, guys, not the primary. Divide this by the Z. Z impedance in percentage. That's kind of the rule. So the I secondary was 601. The impedance as a percentage converted into decimal, 0.05, was it 5, right? And that will get me a healthy, I think 12. Can somebody check that one? 12 kilo amp. 12 kilo amp. Who cares? Now, anything on the secondary side, circuit breaker or fuse, they have to be rated for 12 or more. Otherwise, what you're going to have? If you have a short circuit, bam, big ball of fire came right into your face. Gentlemen, that's all we have. In terms of calc, easy. I need 15 minutes for the theory, and then I'll let you go. Shall we have 5 minutes break? Just readjust. Thank you.